Hello, this is Mr. Craig, and this is the video for the review sheet just before the quiz, day 84, part 4, where it says do this. And the reason why I made this worksheet up, I made it up a couple of years ago when I noticed that some of the students were having difficulties with acids and bases dealing with salts. And so hopefully this making of this video will help you where the review sheet kind of helped them a little bit. So I hope it helps out a little bit. First thing is I want you to list all the strong bases and strong acids using only your periodic table. And the reason why I want you to get used to knowing how to identify strong acids and strong bases with the use of your periodic table is because the periodic table will always be in front of you. So whenever you take a quiz or take a test or have the homework out, hopefully the periodic table is out in front of you. So you can look at it and say, oh, okay, if I know my strong acids and strong bases, I really don't have to memorize more than 3 things. So recognizing that I've got lithium, sodium, potassium, rubidium, cesium, and francium, these are the group 1A metals, and those, when you put a hydroxide on, according to the solubility rules, they're strong. So group 1A, and then from calcium on down, calcium, strontium, and barium, those are the others that we want to look at or be concerned about when we're saying or identifying our strong bases. Now, on the other side of the periodic table, we've got chlorine, bromine, and iodine. So if you put an H in front of the Cl or the H in front of the Br or an H in front of the I, those are 3 of your 6 strong acids. So right now, you've already identified, or you should be able to identify, your strong bases from group 1A and calcium on down, though these are the metals. These are the positively charged particles in your salt. And then the negatively charged particles are the chlorine, bromine, iodine, plus 3 others, which are polyatomics. So you have your sulfate, which is your SO4, but you got to have sulfuric acid, H2SO4. Nitrate, which is NO3, and then the other one is the nitrate is perchlorate, ClO4 with a -1 charge. So looking at your periodic table, you should be able to identify the majority of your acids and bases by looking at the periodic table. So knowing that our acids, again, are hydrochloric, hydrobromic, and hydroiodic, and you just get that from looking at the periodic table. And then you also have sulfuric, which is H2SO4. That's our only polyprotic that's a strong acid. Now do also realize that all of these acids only lose 1 hydrogen. So even though this sulfuric acid has more than 1 hydrogen, it only loses 1. And that's the whole theme for acids and bases. When we talk about acids, we're losing 1 hydrogen. When we talk about bases, it's gaining 1 hydrogen, if it's a weak base. Now, these bases over here, the strong bases, they don't have any hydrogen that they're losing or gaining. Okay, so then the other 2 are nitric acid, HNO3, and the 6th one, and you only need to know 6 of these. So really, you should be able to memorize these 6 strong acids. And then the bases, it's just lithium, sodium, potassium, rubidium, cesium, francium, okay, and then there's OH behind them all, okay, so, but really what I want you to know is not that it's these equations here, but I really want you to know the metals. You've got to be able to identify the metal so that when we make a salt or we have a salt that starts with one of these, or the other ones, calcium, strontium, and barium, okay, now realize that they have a +2 charge, but really it doesn't matter because they dissociate completely. So the only thing that you really need to focus on there is that they have a +2 charge. But when they form a salt, okay, do realize that that's going to break away. All right. Then over on the acid side, I don't care that you know that hydrogen's in front. It's nice to know that. But we really need to know these as our nonmetals. So chlorine, bromine, iodine, nitrate, perchlorate. And then with this, the sulfuric acid, actually it's HSO4 with a -1 charge. So we only lose one hydrogen, but this is the non-metal that I want you to know, just like with those non-metals. So these are probably the most important thing when you are asked to memorize strong acids and strong bases, because when you're given a salt, you need to be able to identify the strong. If you can't find the strong, you're in trouble, okay? There's no way you're going to be able to answer these questions, and you have to be able to find the strong. You're never going to have a week with a weak. That's not going to happen. All right, so looking at the next part here, and actually, yeah, I can do these real quick. All right, you will have some questions on the quiz that ask you this format of a question, and you didn't do very well on. Most of you did not do very well on the quiz when it came to answering this. And I even went over it on the other video that I had for the review sheet right before the quiz. I also talked about it literally minutes before the quiz. And I even made the comment when I was going over it in class saying that water is not an option when you look at these things. So when you read this question, this is how you're supposed to read this question. Like looking at this first one here. The question wants to know, what is the conjugate acid for this right here? So what we need, the way we need to really phrase this is, what is the conjugate acid for this base? Okay, so if it's asking for a conjugate acid, you have to recognize this is the opposite of what the question is asking. So if this is acting like a base, it is accepting a hydrogen. All right, so and somebody today in class mentioned this, and it's kind of cute. Put the BBs together and put the AAs together. It said that acids adopt. I'm trying to remember what it said. Oh shoot, I'm not gonna butcher that. Sorry, but what we need to realize is that bases accept hydrogen ions, and acids donate them. Okay, so when we look at that, we're actually looking for the opposite. And do realize that when you look at these answers, it's the difference of one hydrogen. The base will accept one hydrogen, the acid will donate one hydrogen. Therefore, the charge will change by +1. We'll either add a +1 to the compound, or we'll remove a +1 from the compound. So you have to be aware of the charge as well. You will lose points if you don't have the correct charge. And I know that a lot of you are like, charges aren't that important. They're very important. And I want you to realize that the charges are important just as much as the answer. All right, so when we read this question, conjugate acid for this base. So since it's a base, it accepts a hydrogen. That's why we have one hydrogen here and two there. We have a -1 charge here where we don't have a charge there, because a -1 plus a 1 equals 0. Okay? And I think that was the example that I gave you. Let's come down here, and actually let's look at these. Now I'm going to go across in this direction here. So let's do this. All right, and I'm not going to work all these out because I want you to, I really want to focus on the salts with this video. Because the conjugate acids and bases, we talked about that for the last quiz, and this is something you should know right now. All right, so conjugate acid for this base. So again, if this is acting like a base, it's going to accept a hydrogen. Now you don't have to draw that unless you want to. Now, and another thing is, I don't care if you put the hydrogen on the front, I don't care if you put it on the back, it doesn't matter. Just don't put the hydrogen in the middle. Now, we haven't talked about organic chemistry yet, but I don't think it's really that big of an issue if you put the hydrogen on the back. So it actually goes on the front, but if you put it on the back, that's fine. Also, do be aware of what the charge is. So since I'm adding a +1 charge to this -1, I should have no charge on my H2CrO4. All right, let's look at the one right next to it. It wants to know, what is the base for this? Okay, so what is the base for this acid? So if this is acting like an acid, it's going to donate a hydrogen. So we'll have one less hydrogen. So you should have HPO4, since it has a -1 charge and it lost a +1, it should be -2. So be aware of the charges and kind of keep in mind what the charges are. And if you need to do this, go, okay, well, it has an initial charge of -1 and it lost a +1, therefore it equals -2. There's nothing wrong with doing that if you need to do that. Also, you'll have your calculator on this quiz, so if you need to do that as well, that's okay. All right. Coming across, it wants to know what is the conjugate base for this. So what this is acting like, now, if it's asking for the conjugate base, this is acting like an acid. Okay, or, yeah, and notice that this is the same as this over here. So over here is acting like a base, over here it's going to act like an acid. And how are you going to keep that straight? Well, you're going to read the question, because all of these things on this chart are amphoteric, which means it can act either as an acid or a base. What I don't want you doing is saying, oh, there's a hydrogen on the front of that, and it's going to act like an acid. Well, sometimes it will, sometimes it won't. So since this is acting like an acid, it's going to donate that hydrogen, and you're going to have a CrO4 with a -2 charge. So again, it's giving away a +1 charge, has a -1, so it loses another one, or +1, so it's going to be a total of -2. All right, looking at the last one in this row, question wants to know what is the acid for this base. Notice over here, it acted like an acid. Over here, it's acting like a base. So if it's acting like a base, then it's going to accept a hydrogen. So if it accepts a hydrogen, we're going to put it right on the front, or if you want to put it on the back, that is fine. But do be aware of what the charges are. So if it has a -1 charge and it accepts a +1, we now have no charge up here. Okay? All right, let me work a couple more out here. I've got a few more blanks. Let me clear that palette off here. All right, let's look down here. Okay, the HSCN. Whoops, let's go back up. It wants to know what is the base for this. So what is the base for this? Conjugate acid or acid, doesn't matter. Again, conjugate acids behave just like acids. It's just a matter of where it's at on the equation. Okay, conjugate just means it's on the product side, but it still acts like an acid. Conjugate bases just mean the bases are on the product side, but it still acts like a base. So in this case here, it wants to know the conjugate base, or I'm sorry, the base for this conjugate acid or acid. What do acids do? They donate hydrogen, so you're going to be left with CN, and since it had a -1 charge and it lost a +1 charge, -2. Coming over to the next one, it wants to know what is the conjugate base for this acid. So in this case here, since it's acting like an acid, it's going to lose a +1 charge or a hydrogen. And so now you'll have C2O4 with a -2 charge. That's a polyatomic, but not one of your 10, which is oxalate. All right. Looks like I got maybe one more that I have empty here. Wants to know what is the conjugate acid for this. So this is acting like a base. What do bases do? They accept. So we'll put the hydrogen on the front. So H2CrO7. And since it had a -1, there should be no charge there. All right. I hope that helps. Let's do one more here. This last one is asking the acid for this, so it acts like a base. So that means that the hydrogen is going to be donated or accepted onto this. So we'll put the hydrogen on the front, H2SO3. So that's sulfurous acid, which is also weak. Okay, now let's get to the fun part. So knowing your strong acids and strong bases, this is why you want to know this, just for this question right here. Number 3 says, write the dissociation reaction for each of the following salts when placed in water and determine if the solution will become acidic, basic, or remain neutral. And then it says, then identify the thing that causes the solution to become this way. All right. So when we talk about thing, we're talking about the ion, whether it's the nonmetal or the metal that causes it to become acidic or basic. If it remains neutral, there's no thing causing it to change because it is water, has a pH of 0. All right, so here's what we need to do. We need to identify the strong. You've got to find the strong in all these salts. And probably that would be the first thing that I would do if you're ever posed with a question like this. So looking at this first one, I notice that I start off with a carbon. So that tells me right there that I do not have a metal from group 1A or from calcium on down. So I need to look on the tail end of this salt and find something that's either perchlorate, nitrate, so HSO4 with a -1 charge, bromine, chlorine, or iodine. Well, when I look at it, I find iodine. Okay, not HI, just the iodine. So we're going to take this salt and we're going to dissociate it. Okay, and it's going to dissociate into C4H4O2H with a +1 charge and iodine. Now, recognizing that the iodine is a conjugate of a strong acid, it does nothing. So absolutely no way is the iodine going to cause this solution to become acidic, basic, or remain neutral. So this is the thing that causes it to become either acidic, basic, or remain neutral. Well, I can tell you right now it's not going to be neutral, because the only time that it remains neutral is when you have a conjugate of a strong acid with a conjugate of a strong base. We don't have that. We only have a conjugate of a strong acid. So since the front end of every one of these salts, especially like this sodium C3H7O2 is, the front part of this will always be, actually let me do that over here. The salt will be broken down into two parts. You will have your metal on this side, or your positively charged ion, and then you'll have your non-metal on this side. Nothing's changed, or your negative component. This will be a conjugate of some kind of base. Okay? Notice how I'm saying that. A conjugate of some kind of base. Could be strong, could be weak. This is going to be, on this side, or the non-metal, will be a conjugate of some kind of acid. Okay? So a conjugate, put conjugate over here. So conjugate of some kind of acid. If it's a strong acid, man, we can cross that off. If it's a strong base over here, we can cross that off. So the metal and the non-metal are the conjugates of some kind of base and some kind of acid. So recognizing that the iodine is a conjugate of some kind of acid, in this case a strong acid, we can throw that out. We found our strong. So therefore, this part of the salt is a conjugate of some kind of base. Recognizing that that is not lithium, sodium, potassium, all those in group 1A or calcium on down, this is the thing that's responsible for this solution to become either acidic or basic. Now you have to ask yourself, what do conjugates of bases behave like, or what are they? Well, if we have a conjugate of a base, it behaves as an acid. So this is, when it's placed in water, is going to donate a hydrogen. So a hydrogen will break off from this, and you'll have C4H4O2, H with no charge. Notice that the charge is equal on both sides. So this is the reason why the solution became acidic, and the reason why it's acidic is because we released hydrogen into the system. Okay? All right. Let's clear the palette. Let's take a look at the next one. Okay, and I may use this room up here. So we have, for this, we have CS2SO4. Split that salt right down the middle. You got to. So we have to identify where our strong is at. So recognizing that we have CS, which is, again, looking at our periodic table, cesium right there, okay, that is in group 1A, clearly. So when we dissociate this, you'll have two cesiums. Don't put a subscript on that. That is not what we do. And SO4. Now, some of you may think, oh yeah, okay, great, fantastic. We have, this is a conjugate of H2SO4. Actually, it's not a conjugate of H2SO4. A conjugate of H2SO4, come on, pen, right. A conjugate of H2SO4 is the hydrogen breaks off, and you have HSO4. And HSO4 is a conjugate of sulfuric acid. However, we have SO4. So what that means is when this salt dissociates, the cesium does nothing. However, the sulfate is going to behave as a conjugate of this side, which again is a conjugate of a base. I'm sorry, a conjugate of some kind of acid, which behaves as a base. So when we place this in water, water is going to rip a hydrogen off, and we're going to form HSO4 with a -1 charge and hydroxide. So the thing that causes it to become, in this case, basic is because of the SO4 with a -2 charge. Okay? The hydroxide doesn't make it basic, it's this thing. As it rips the hydrogen off of the water, it forms hydroxide. That just makes the solution basic. It's not the cause. The cause is this guy over here. All right, let's try another one. We have CH3N2HNO3. All right, again, find where their metal ends. Actually, find where your strong is at. So there's where you split it. So when this thing dissociates, we've got CH3N2H with a +1 charge plus NO3 with a -1 charge. Nitrate is a conjugate of nitric acid. This does nothing. However, this is a conjugate of some kind of base, which behaves as a acid. Very good. So CH3N2H plus is the reason why this solution became acidic, because when it dissociates, it's going to form a hydrogen ion and the CH3N2 with no charge. Okay, so this is the cause for the solution to become acidic. And that's huge. You've got to be able to find the strong. All right, let's clear that one. All right, RBF. Okay, RBF. I want you to split it. And then here's something that I heard a couple students saying. I was like, you might want to look at your periodic table again. When we look at the periodic table, okay, we know that chlorine, bromine, and iodine are components of strong, but fluorine is not. Fluorine is not chlorine, bromine, or iodine. So when we look at RBF, okay, we know that the rubidium is, because it's a group 1A metal. So when this thing dissociates, we have rubidium plus fluorine, but fluorine is not a conjugate of a strong, only the rubidium. Therefore, the fluorine, when placed in water, okay, it's a conjugate of some kind of acid which behaves as a base. So we're going to rip that hydrogen off, and we're going to make HF and hydroxide. So the thing that is responsible for this solution becoming basic is the fluorine ions. Okay? So again, it's all about where your strong is at. Okay? All right, let's look at this one. Find your strong. And if you need to pause the video at any time to do this, I would highly recommend it. Try it before listening to me. Okay, here again, boom, there's our separator. So this part is a conjugate of some kind of weak. This is the conjugate of our strong. So there's our strong component. So HNNH2Br associates into NH2 with a +1 charge and bromine ions. And again, the bromine does nothing. Ignore it. It doesn't go away. So this is the cause of our solution becoming acidic. Okay? So when you place that in the solution, 2 with the +1 charge, it breaks off into a hydrogen. I hope I've been writing double arrows on the rest of these. I apologize if I haven't. NH with no charge. Okay, so that is the reason why the solution became acidic. All right, let's look at the next one. Here we have barium acetate. Boom. Find your metal, find your nonmetal. Okay, the barium is a conjugate of one of our strong bases. Now don't freak out just because we have 2 acetates. Life is still good. Okay, so the barium +2, and again put that 2 in front of the acetate, C2H3O2. So the barium does nothing where our 2 acetates, and if you only want to use 1 acetate, that's fine. Actually, let's just use 1. But some of you might be upset and not be able to do 2, but that's okay. So this is a conjugate of a weak acid that behaves as a base. So we're going to rip hydrogen off of this, and we're going to form acetic acid. So this will cause a solution to become basic, because C2H3O2 and OH, and this is the cause for the solution to become basic. Okay, all right, let's look at the next one. Here we want to split it here. So we have our C5H3N3H with a +1 and chlorine. Again, recognizing chlorine's one of those 6 from our strong acids. So the C5, it's this guy, the C5H3N3H plus, when it dissociates, it's going to break off a hydrogen. and cause the solution to become more acidic. Okay. All right. Now the last one that's on your worksheet, and I have some extras here to let you try. The last one here is very, very interesting. We have our metal and our non-metal, but we have rubidium and we have chlorine. Okay. Now a lot of us get in the habit of whenever we find our first strong, we stop. You still have to be checking to see if you have two strongs. And rubidium, again, whoops, where'd you go? Rubidium is in group 1A, where chlorine is also one of our conjugates of a strong. So we have two things that are conjugates of strong. Therefore, it remains neutral. Okay? So the pH remains 7. It doesn't change. All right, I hope that made sense. All right, try a couple of these here. And some of these might be salts, some of these just might be acids, some of these just might be bases. Okay? Go ahead and pause the video and give it a shot here. Okay, you've had a chance to try it now. Hopefully you recognize that this is a strong acid. So the hydrogen breaks away from the perchlorate. Again, the perchlorate does nothing. The hydrogen causes the solution to become more acidic. Plain and simple. So that's not a salt. All right, the next one, there's your perchlorate. Same thing there. So since we have a conjugate of a strong acid and then we have a conjugate of some kind of base, this conjugate of the base behaves as an acid. Very good. Now, don't freak out and go, whoa, wait a minute, it's got a hydroxide on the end of it. Yeah, it doesn't matter. Again, it might look like a hydroxide to the untrained eye, but it's not. So perchlorate does nothing. However, the CH2OH only loses one hydrogen because of the nature in which it is. Okay, so this is what causes the solution to become acidic. Don't fall for the trick of there being an OH on the back of that. Okay, there's a lot of organic compounds that have hydroxide, or what appears to be hydroxide on the end, and it does not cause the solution to become basic. So don't fall for that. All right. Oh, okay. And then here, identify your strong. Very good. So you got your iodine. So the iodine doesn't do anything. So your HCH3SH plus 1 and iodine. Okay, the iodine doesn't do anything. So the solution becomes more acidic because the conjugate of a strong acid does nothing, where the conjugate of a base behaves like an acid. So it dissociates. Hope you guys are getting bored with this. Dissociates a hydrogen ion. So we have our hydrogen plus our HCH3S. Yeah. All right, I think I've got a couple more here. Oh boy. All right, I'm actually not going to do those, but if you want to try those, and here I'll blow through them real quick. You can try these, and I'll verbally tell you what the cause is. I'm not going to write it down. Our strong is right here. So this will cause the solution to become basic. Conjugate of a strong base means that we have a conjugate of a weak acid. A conjugate of a weak acid behaves as a base, so this will be a base. Here we have a strong base, sodium hydroxide. Very basic, but there is no cause for this. It's not a salt. It's actually a strong base. We have potassium acetate. Potassium does nothing. The acetate is a conjugate of a weak acid that behaves as a base. The solution will become basic. On the end here, we notice that we have the chlorine. The chlorine is a conjugate of a strong acid. This is a conjugate of some kind of base. Since it is a conjugate of some kind of base, it behaves as an acid. The solution becomes acidic. This is a conjugate of a strong with a strong. It remains neutral. Rubidium fluoride. Oh, I thought we just had that up here. Nope, that was rubidium chloride. Okay, so in this case, the rubidium is the reason why we don't do anything, but the fluorine causes the solution to become basic. Fluorine is a conjugate, rubidium is a conjugate of a strong base, which does nothing. Fluorine is a conjugate of a weak acid that behaves as a base. So it'll accept the hydrogen off of the water to make HF. And usually, well, actually always, these will make weak acids. And remember, man, my pen is not wanting to work very well. So that's the reason why these are so nice. HI, we have our strong acid. So the iodine doesn't do anything, but the H causes the solution to become acidic. Our bromine is a conjugate of a strong acid, therefore it does nothing. On this side we have a conjugate of a weak base that behaves as an acid, so the solution becomes acidic. Potassium hydroxide is a strong base. Lithium is a conjugate of a strong base, therefore this is a conjugate of some kind of acid, therefore conjugates of acids behave as bases. Francium is a conjugate of a strong base which does nothing, therefore the C2H7 is a conjugate of some kind of acid that behaves as a base. Alright, hopefully you guys are getting the knack for these salts, and I promise on the AP exam it'll throw a salt at you. It probably won't even tell you it's a salt. It'll say, what will the solution, if you have pure water and you place this salt in the solution, will it become acidic, basic, or remain neutral? Okay, so be prepared. That's very typical. That's what's asked at the AP exam. All right, let's look at number 4. It says calculate the pH of a 0.677 molar rubidium, whatever that is, solution, and then it says a Ka value for this. Okay, notice that you're given a 4 value here. Okay, you like that? A K value for something. So I gave you a K value for something you don't have. So just like what we did in the previous problem, we need to recognize that this is a salt. So the salt, the rubidium, does nothing. Therefore, this is a conjugate of this weak acid. Therefore, this behaves as a base. Knowing that this behaves as a base, we're going to have our our C3H3N2, which has a -1 charge, is going to react with water to form this. So we'll dissociate and we'll have this. So the solution will become basic. Okay. Now, I've already got my ice chart. We know our concentration is 0.677, and that's all we know. So this is what we're going to do. You may use the 5% rule since we have 0. We would not use approximate 0 here because we don't have a solution that's at equilibrium. We're actually taking this salt. Okay, we have our pure water. Okay, so our pure water with a pH of 7 before we drop our salt into this. So after we drop the salt into this, then the pH should change a little bit. Okay, so after we drop it in, okay, after pH is what the question's asking for. So it starts off at a 7, and then we're going to drop this salt into the water, pure water, which has a pH of 7. So we want to find out what that is. So you were given a Ka value, so knowing that this acts like a base and forms hydroxide, we need a Kb value. Also remember, hydroxide is always on top whenever you have a Kb value. Okay, so we have to calculate our Kb from our given Ka. May use 5% rule, so drop the X. And then we can solve for the hydroxide concentration, which will give us our pOH. And then if you choose to, you probably go right for it and solve for your pH. Now do notice this, that the pH did start off at 7 when you added a base. Okay, and this is really important. This is a real quick check. That when you add a base, should the pH go up or down? It should go up, because that indicates that the solution is becoming more basic. Okay. All right, number 5. I want you to find the pH of a solution that has 44.5 grams of rubidium hydroxide dissolved in 4.75 liters of water. Now, this is another question where it's not coming out and it's not telling you a couple things. You're not given a Ka value or a Kb value. You're not given any kind of K value. You want to know why you're not getting a K value? because you must recognize what this is. If you don't know what that is, you're dead in the water. Okay? So rubidium hydroxide is this. And when you write it out, hopefully it'll go, oh my gosh. Oh my gosh. If I go and look at my periodic table, I notice that rubidium is right there. So if rubidium's right here, I have a strong base. So I don't want a K value. If I have a K value, that means I have a weak base. Okay? So realizing that you have rubidium hydroxide, which is a strong base, then we need to find out how many moles of the rubidium hydroxide we have. Also, if this is a strong base, what does that tell us about the base? Well, it's strong, therefore it dissociates 100%. So if you have a strong base that dissociates 100%, and I just found the concentration to be this because I found how many moles divided by my total volume, if this dissociates 100%, do I care about the concentration of rubidium? Not really. I care about the concentration of rubidium hydroxide because that'll tell me what my concentration of hydroxide is. If I know what the concentration of my hydroxide is, bam, I can find pH or pOH, depending on what the question's asking. But this whole question is more of a concept than it is a math question, because everybody should be able to convert grams into moles, and everybody should be able to determine molarity. And I was a little surprised and a little upset how many of you had forgotten what molarity is. Okay? Now, what we would not do is start with the 4.75. The only time that we start with the volume is if we know this value. We are calculating this value. Okay? So there's a big difference of knowing and calculating it. All right, so the big concept for this question is that rubidium hydroxide is strong and dissociates completely. All right. Number 6, calculate the pH of our solution here, and you're given a Kb value for something. Again, knowing that this is a salt, recognizing the strong within the salt. Also, realize that if I'm giving you a Kb value, this thing better have one more hydrogen within it. So I see 6 hydrogens here, I see 7 there. That's good news. So when this salt dissociates, and yes, you do want to show the dissociation of this salt. So, and again, it's worth a point. So, easy point. All salts are strong, so it does dissociate into HC7H7, and it will have a +1 charge, and then the perchlorate with a -1. Perchlorate does nothing, so we don't need to worry about it. However, this guy we do want to worry about. So we have our HC7, H7 +1. Double arrow it because it's weak, because that's not one of our strong. And it forms C7, H7. And if you took it off of the back, that's fine, just as long as you're not taking the hydrogens from the middle. And notice that there's no charge on this one. All right, so once we have this, there's our equation. Actually, here, let me write it the same way that I have it on here, so I don't want to confuse you guys. Oops. Okay, let me put that. So put the H here, and we'll have a 6 here. And it doesn't matter from which side you take it from. All right, so we start off with zeros. We have our 3.44 because that's given. Okay, so we have our 3.44 molar solution. However, do realize that since we do form hydrogen here, and you're given a Kb value, we need to find Ka. Okay, so there's our expression based on our ice chart. Your Ka, again, Kw over Kb. You may use the 5% rule, and there's our pH. Okay, so again, not too difficult, I hope. All right, let's look at the next one. Number 7. Says calculate the equilibrium constant K for at a certain temperature for the reaction that's given here. It says if the initial concentration of lactic acid was 4.33, when the reaction reaches equilibrium, it's discovered that the lactic acid dissociated 0.677%. All right, so again, I might be able to do this. So since we had our equation where our hydrogen ions at equilibrium over our acid initially times 100 is equal to our percent. Probably the best way to do this is, since we know what our percent is, we're going to divide 100 on both sides. We're going to multiply our initial concentration of the acid, and we'll rewrite this as our hydrogen concentration at equilibrium is equal to our percent value, whatever that number is, so that's some number, times our HA concentration initially divided by 100. Okay. Now, some of us automatically went ahead and just said, oh, I'm going to move the decimal place over 2 places. That's fine, not a problem, but don't forget to multiply the 4.33 by that. Okay, so that's where this is coming from. So we get our concentration, and actually this is equal to X. So if you know that that's equal to X, we can plug that right in. Knowing the value of X, we don't want to use 5% rule, so we'll get some exact values here. I may have rounded a little bit here, but that's okay. If you want to leave that exact value in your calculator, you may very well do so. Nothing wrong with that. Plug the values in. So here's your Ka, which is 1.996 times 10 to the negative 4. I'd be careful in rounding just yet. You don't want to round too quickly here. All right, so there's our Ka. Part B says calculate the pH of a solution formed by dissolving 123 grams of francium lactate. Hopefully you recognize that this is a salt. So when the francium lactate, Fr, C3H5O3, okay, so the francium is a conjugate of our strong base. It's a salt that dissociates completely. And we have our C3H5O3. So this is our conjugate of our lactic acid. So this is a conjugate of an acid, so this behaves as a base. So when we figure out how many moles and what the concentration is, we're going to place this base in water. And what will bases do when they get in water? Well, they'll rip off hydrogen and will form our lactic acid. Okay, so it's a common ion. This is a common ion of what we started with, and hydroxide. So since it forms hydroxide, it causes the solution to become a little more basic. So our ice chart will resemble that. And again, I do have approximately 0 on there. You know, I have a lot of students ask, do you have to have that on there? It's a good idea to have it on there, but I hate to tell you, we only care about at equilibrium. So even if you just made an ice chart that just showed at equilibrium, nothing wrong with that. All right, and then so since it is a hydroxide, we want to find out what the Kb is. May use 5%, and then we're going to take this, multiply it over here, divide that over here. So that's how we got this value here. Okay, and then if you have the hydroxide concentration, you can find the pOH, thus finding the pH. All right, then number 8. This is just using your calculator. Again, if you're given a pH and you want to find the hydrogen concentration, so I know this and I want to know what this is, then to go from here to here, I'm going to take my anti-log of my negative pH. Whoops, what happened there? Negative pH. And now it'll give me my concentration. Excuse me. And then if I want to go back this way, in other words, I know this and I want to find the pH, then I take the negative log of this value of the concentration. Okay? And then vice versa with the hydroxide and the hydrogen. So the hydroxide and the pOH, I'm sorry. Now, to determine whether this solution is acidic or basic, there's many ways that you could do this. You could look strictly at pH. If pH is greater than 7, you got a basic solution. If pH is less than 7, okay, you got an acidic solution. If you have pH is equal to 7, it's neutral. Okay, so that's one way. Another way is you can compare these two. This represents for the acid, this represents for the base. Whichever of these two values is smaller, so that one's smaller, should be basic. Okay. Or when you look at these two values, again, the hydrogen represents for the acid, the hydroxide represents for the base. So whichever of these values is higher represents for the acid or the base. So it's lower over here, higher over here. So in this case, the hydroxide has a higher value, therefore it's still basic. Okay? Hope this video has helped. If you have any questions, please do not hesitate to email me.